Okay, so I'm told we should start. Good morning. So let me start by reminding you where we stopped yesterday. I'll just kind of continue on. So the big questions that I was trying to tackle were basically two types of questions. The first one is, how does the structure of networks impact outcomes? And in particular, we wanted to know kind of questions about outcomes with respect to within and between networks. That is, we want to look at behavior and welfare, both in different locations within a network and also when you compare different architectures of networks. So that's the first class of questions, the main one that I wanted to tackle. The second one is, how do these networks form to begin with? So I described to you yesterday different types of networks. We saw that they look very different in different contexts. So we want to think a little bit how these networks form, especially given that they ultimately may impact the outcomes that the agents who participate in them experience. So basically what I'll do today is continue answering the first set of questions, continue the model that we started yesterday, and then hopefully I'll have enough time to give you some flavor of the types of models that we have in the network formation literature. Okay, so just to recap on the model that we had, I'll start from the beginning, but I'll go over it very quickly just so that you have it in your mind. So we had a situation where we have a network that's captured by an adjacency matrix. So this is just a matrix that has these dummy variables. If I and j are connected, it has the value of 1, otherwise 0. Nij just corresponded to i's neighborhood, so that just includes all of i's neighbors according to the network. Dig is the degree of I, the number of neighbors that I has. And each player in our game chooses an action in 0, 1. Okay, so this is a restriction, the first restriction that I imposed, just to make the presentation simple. In general, you could think about more general games. Payoffs in our game for today depend only on the number of neighbors choosing 0 or 1. We normalize the payoff of all neighbors choosing 0 to 0. And in fact, if you chose 0, your payoff was normalized to 0. So that's how I normalize things. And if you chose 1, then you got this value that depended both on your degree D and on the fraction of agents in your neighborhood that choose the action 1, and on your idiosyncratic cost. Okay? So this is the main thing to remember. So if this is greater or equal than 0, you choose the action 1, and otherwise you choose the action 0. Okay? That's basically the simple decision that each agent makes. What we're assuming is that this function is increasing in x. And this is what us economists call positive externalities. So if more people around you are choosing the action 1, your payoff increases. Ci, the cost, the idiosyncratic cost, is distributed according to age. So you can think about it as kind of the value of learning a new language. That depends on how many around you. If you're thinking of learning German, how many around you are speaking German, and how hard it is for you to learn a new language, okay? Which is a personal thing, and there's some distribution to it. So some examples that we discussed, I won't go into details because we talked about it yesterday. This could capture a situation where your utility comes from the average action, from the total number of people who are actually choosing the action 1. It can be something like a threshold, like we talked about political revolutions, where you need a certain number of people to choose the action 1 with you to revolt in order for this to be effective, and so on and so forth. G is drawn from a set of networks that satisfy several conditions. So first of all, we assume that the degree of neighbors are independent. That's a pretty harsh restriction. In general, you can relax that. It requires some technicalities, so I'm not going to go into it today, but if you're curious, you can ask me later on. The probability of any node having degree D is going to be P of D. And the probability of a given neighbor having degree D is therefore something that's deduced from the little p distribution. Okay, so little p is always going to correspond to the underlying degree distribution, and big P is the neighbor's distribution. Okay, so maybe I'll keep that on the board. The basic one, and P of D is the neighbors. P of D over the expectation of D. Namely, the way we talked about this yesterday, but just to remind you, basically if I'm connected to someone, I can update on their degree because I know they're connected at least to one person. So in some sense, I need to update on my belief on their degree distribution. And ultimately, the place where we ended last time was this fixed point equation that characterized the fraction x of neighbors choosing 1. So what does it have here? Let me just write it because we'll use it later. So keep that. So we have x, which is equal to d, pd over d of d. This is just the distribution of neighbors times h of v of b of x. And this is we call phi of x. So this thing, where is this coming from? This miniature monster is just the probability that v of dx is less than c, right? So this is just the probability that a random neighbor of mine chooses the action 1. Because that's the value that any neighbor gets if they're of degree d, and that's their cost. So the probability that the value is lower than the cost. Sorry, this is reversed. Beautifully. The cost is lower than the value is just a h of vdx. Right? This is just because h is the cumulative of the cost, right? And then I'm just weighting it by the probability of each neighbor having degree d. Okay. Does this make sense? Because this is what I'm going to work with now, so this is sort of important. Okay, so I've rushed through it. If there are any questions, please let me know. All right, so first of all, a fixed point exists, and this is a simple intermediate theorem at play, because if everything is well behaved, notice that if you apply the right-hand side is always non-negative, so if you plug x equals to 0, the right-hand side should be at least 0, and if you plug x equals to 1, the same thing holds, the right-hand side is at most 1. So the intermediate value theorem guarantees that we're going to have a fixed point. So there's no problem of existence here. If h of 0 equals to 0, x equals to 0 is a fixed point. Okay, so no one adopting essentially is a fixed point. This is going to be sort of an important fixed point because this is a situation where nothing spreads in a way. So this is a biggie. Okay, so what I'm going to do now is start talking about the characterizations of equilibria here. So first of all, what can we say about any symmetric equilibrium here? Well, it's non-decreasing in degree if this v is increasing in d. Okay, so if your value from the action 1 is increasing in your degree, then the higher your degree, the more likely you are to choose the action 1. You get a higher value from it. So this is not a very profound statement. And likewise, if v is decreasing in d, then your likelihood of choosing the action 1 is going to be decreasing in d. Okay? So the monotonicity of the equilibrium structure follows the monotonicity of this value v. Okay? And expected payoffs move in the same direction and much the same way. And again, the intuition is that in a symmetric equilibrium, a random neighbor has probability x of choosing 1 and a probability 1 minus x of choosing 0. So let's do it a bit more formally than what I just said. If you consider an agent of degree d plus 1, if v dx is non-decreasing, then the payoff from action 1 here is going to be higher for an agent of degree d plus 1 than for the agent of degree d, right? And that means that they're more likely to choose the action 1, right? They'll be able to choose the action 1 with a lower cost. And similarly, if v dx is non-increasing. Okay, so this was kind of the static way. Now I'm going to transform this into a dynamics. Okay? So the way I'm going to think about it is that we start out with some x0, and then the next x that we're going to choose in the population is just going to correspond to this phi of x0. Okay? So basically, xt is just going to correspond to phi of xt minus 1. Okay? So this is almost like a fictitious play. Those of you who've seen this, it's as if you observe the statistics from the population from last period, and you're best responding to that. If you're doing that, this is the type of dynamic that will emerge. So this is a dynamics that's very simplistic in many ways, because it assumes that you observe only kind of an aggregate statistics, and it assumes that you're very myopic. You're not doing anything strategic with respect to the future. You're not trying to affect kind of future actions in any way. What are some possible interpretations? I think there are two main ones that are kind of useful to keep in mind. The first one is that you can just think about it as sort of understanding which equilibria are more stable than others. So it's almost like we're doing a little bit, a little perturbation to the equilibrium, and we're trying to look at where will it end up. Kind of will it converge back to the equilibrium we started with, or will it kind of move away? Well, what's likely to happen? A different way to think about it is really more seriously as diffusion. So if you wanted to take it more seriously as a diffusion process, it basically means, like I said, that we're looking at the best response structure where there's a large and very well mixed social network. And for those of you who have worked in these fields, this is sometimes referred to as the mean field approximation. So it's basically as if you're looking at the statistics that you observed from last period, and you assume that even your local neighborhood emulates the field. It's just as if it was taken as a sample from the entire field. Now, these are approximations that I hate teaching. They provide really cool results, but they're horrible to teach because not only are they approximations, but they're approximations where we don't really have theoretical results about how good the approximation is. So what people often do is basically run simulations and check the approximation as opposed to your original model, whatever it is. But that sort of with a theory hat, this is a bummer in a way. So thankfully I don't have time and I don't have to suffer through that, but just as a warning sign, this is something to keep in mind. Okay, so let's look at this function phi of x, and now the way I drew it is I'm drawing xt plus 1 on the y-axis and xt on the x-axis. And notice that equilibria, we know, are situations where this phi of x precisely crosses the 45-degree angle line, right? Because in that case, xt plus 1 is going to have converged in a way. It's going to coincide with xt. That's precisely the point in which this fixed point equation holds. Does this make sense? So when we look for equilibria, we're basically looking at this graph and looking for points that intersect the 45-degree line. Now, as it turns out, this graph is going to capture all the information. So from now on, I'm basically going to play around with this graph, and that will give me a lot of comparative statics that come out. Now, it's important to notice two types of intersection points that we'll have nicknames for. The first one is a situation where the crossing is first below the 45-degree line and then above the 45-degree line. That we'll call a tipping point or an unstable equilibrium. Why do we think of this as a tipping point? Well, let's think about a situation where you perturb the equilibrium a little bit and start from an x0, which is just a tiny bit to the right of the equilibrium. So notice that x1 is just the image through phi of x0, and that's going to be this x1. Okay? Now that's above x0, so therefore when we move to the next period, x1 is going to be to the right of x0, right? And x2 will be just the image according to phi. That jumps up even more, right? And we can continue this till we reach the next equilibrium up. Okay? So in that sense, it's a tipping point because you perturb the equilibrium by just a little bit, and you're shifting to the next equilibrium. Okay? Through this dynamics. Now, in fact, equilibria that cross the 45-degree line in the different direction, where first it's above the 45-degree line and then it's below the 45-degree line, don't exhibit this sort of explosive behavior. Okay? So I'll let you stare at it and convince yourself. Does it make sense? Or should I draw it? Make sense? Okay. So this we'll call stable equilibria. So basically we have these two classes of equilibria. Ones are tipping points and ones are stable equilibria. And now what we want to understand, just a sec, now we want to understand how these things behave as a function of different attributes or features of the network in place. Yes, Bo.
Could it be tangent to the 45-degree line?
It could, and I'm sort of going to ignore that. So you're right that in principle we could have all sorts of funky behaviors where it tangents the 45-degree line and we don't even get these nice alterations. I'll assume that everything is well behaved for today. You know, this is the generic case basically, so it's, we're not too worried about it. Okay. Other questions, actually? Yes.
Are we losing anything, or are we losing a lot by making x the same fraction for everything? Like, if you only have 4 neighbors, then for every node with 4 neighbors, the fraction has to be one of 5 things. So.
Right. So I won't deal with that right now. I mean, there are some papers that do simulations and try to actually compare things. We haven't done it ourselves, and if I had more time, I would show you figures. So sometimes we know this approximation is not too bad, and other times we just don't know. So there's more to do, yeah, both theoretically and empirically. Yeah.
And so on the same line, so when I choose a neighbor of degree d, then the distribution of its neighbors will be completely different, right? So,
right.
So the fraction of its neighbors that choose 1 will also be not x, right?
Right. So here, this is where the independence comes into play. So, and on that realm, we're not sinning too much because we've assumed this independence, which is a harsh assumption in itself. But that's actually something we can relax theoretically as well. So that's not where the big sins are coming from. But you're right that this is an approximation, absolutely. Okay, so stability at 0. So if phi of x is less than x in a neighborhood around 0, we get 0 as a stable thing. And in general, what we see here is the structure of first tipping points and then stable points. So this is just what I mentioned before. Generically, what we're going to see is the structure where you first have tipping points and then stable points, etc. So anytime if you're drawing this curve that crosses the 45-degree angle line, you're sort of bound to have this sort of structure of alternations unless you have tangencies, as Bo was pointing out. Okay. So now, basically what we're going to do is keep track of how phi changes, concentrating on what I'm going to call regular environments, these environments where we crossed out tangencies. Okay? So we're just going to see, basically, how these phis are changing, okay, as a function of different things. So notice that if phi prime is a pointwise increase of phi, then the tipping points and the stable equilibria are nicely ordered. So we know that the tipping point that corresponds to phi prime is to the left of phi, right? And the stable equilibria move up. So this is going to be at the root of the different comparative statics that I'll describe to you now. Okay? So basically we're going to look for pointwise increases or decreases in the underlying function phi. Okay. First order stochastic dominance shift. This is just a review. How many of you have seen that? Okay, so not everyone. So first order stochastic dominance shift is just a way for us to say that one distribution puts more weight on higher degrees. Okay. Now formally what this means is that P first order stochastically dominates P prime if P of D is less than or equal than P prime for all D. Okay, so this means that the probability of having a degree which is low, which is fairly low, is smaller under P than it is under P prime. Okay, that's why P actually first order stochastic dominates things, even though it looks like it's smaller in the inequality. So this is how it would look, for example. So this is P. It's lying below P prime, but recall that what's the y-axis here is the probability that random degree is less than r degree D. Okay, so this means that higher degrees are getting higher weight under P than under P prime. Okay. Does this make sense for those of you who haven't seen it? Okay. And as it turns out, this is sort of an equivalent notion to the following requirement, that for any increasing function, f of d, if you look at the expectation of f of d under P, it will be higher than under P prime. This sort of makes sense because f is increasing in degrees. If you're putting more weight on higher degrees, then you're going to get a higher number here. All right, so let's consider a first order stochastic dominance shift in the distribution P of D. This is the distribution of neighbors, degrees, and this is going to be important. So this is this distribution, not the underlying distribution. And as an exercise, you can try to find an example in which the underlying distribution, there's first order stochastic dominance in the underlying distribution, but not in the neighbor's degree distribution. So these are not equivalent. So what happens here? If we do a first order stochastic dominance shift in the neighbor's degree distribution, then there's more weight on higher degree neighbors. Now, if VDX is non-decreasing, we know that the higher degree agents are more likely to choose the action 1. And therefore, you have a higher expectation of higher actions. Right? And you're therefore more likely to take the action yourself. Right? Because you're more likely to have more neighbors that are choosing the action 1. Now, notice that kind of formally, so this was the hand-waving intuition, but formally, if VDX is non-decreasing in D, then notice that this function is increasing in D. This is a cumulative distribution function, so it's certainly increasing in the argument. So this thing is increasing in D. And so as you make first order stochastic dominance shift in the distribution, you're going to get an increase in phi. So we're going to get this pointwise increase in phi. Okay? And in particular, we're going to have lower tipping points and higher stable equilibria. Okay? Does this make sense? Okay, so let's take it back to some networks that I've already shown you, just to put some, to drag it back to data. Now, this is not going to be a very applied exercise, but let's compare two very starkly different networks. One is the romantic connection network from the Midwestern High School that I showed you yesterday. So I'm just reminding you the pink dots are girls, the blue dots are boys. I'm going to ignore these two types of agents and just treat it as one big network with one type of agent, with the 1 degree distribution. And the other type of network that we discussed yesterday, that I'm drawing in sort of a different way, is the economic co-authorship network. Okay. This we discussed when we were comparing the economic, the real networks to the Poisson type networks. So this is the neighbors' degrees for the two types of distributions. So what you see here in the top graph, or the green graph, is the neighbor's degrees, this induced neighbor's degree for the romantic network. And with the red graph, you see the induced degree distribution for the co-authorship network. Okay? And as it turns out, the co-authorship network first order stochastically dominates that of the romantic network. Okay, so what you see here is that it puts there's higher density on the higher degrees, and as it turns out, it actually satisfies this nice first order stochastic dominance condition. Okay. So let's look at an example. Suppose that we're looking at a game where you adopt a certain action or product if the chance that at least one neighbor adopts exceeds 95%. Okay? So that's what drives you to buy an iPad. Now if we look at the romantic stable equilibrium, if you solve it out for the degree distribution, you get the degrees 3 and above adopt. And what comes out of it is that ultimately the probability that a given neighbor adopts is 0.65, where the percentage adopting is 29%. If we do the same exercise with the co-authorship network, then you'd see that the degree 2 and above adopt, and ultimately any random neighbor of yours will adopt with a probability of 91%, and the percentage of those adopting will be 55%. And the utility is higher. So if any of you are feeling frustrated that you're working all the time, look at that. Okay, how about raising costs? So far what I did is look at raising the density of network interaction. So we looked at adding more links in a way. This was the first order stochastic dominance shift that we just talked about. Now let's think about raising cost. Raising cost lowers the function phi of x pointwise. That shouldn't come as a shock. So you raise costs, you lower the likelihood of any individual adopting. Right? So that is going to raise tipping points and lower the stable equilibria. So that is going to make it harder for something to spread and make it more robust for things to stay where they are. Okay, so this was kind of a trivial thing. The last type of thing that I want to talk about with respect to comparing different networks is changing their variance. So there are kind of two main things we do to distributions. One is we change how linked they are. This was this first order stochastic dominance shift. And the second one is we change how skewed they are. Kind of, does it matter whether you have everyone with the same degree or some people having degree 0 and some people having a very high degree? Okay? And this is the type of exercise that we'll do now. So a mean preserving spread, those of you who haven't seen first order stochastic dominance, you probably haven't seen that, so don't worry. That's for those of you who have seen it, this is going to be kind of a mean preserving second order stochastic dominance shift essentially. But I'm going to define it now. So if this was a foreign language to you, don't worry. So if P and P prime, P is our distributions, P is a mean preserving spread of P prime, if basically they both have the same mean, and when you looked at the distribution P, you just shifted weights to more extreme degrees. It's as if you stretch the distribution. Okay? That's what it means informally. Formally, the way to define it is to say that the area under the graph P of D is higher than the area under the graph P prime of D, no matter where you stop summing up the area. Okay? Yes?
So this P and P prime are this cumulative distribution, right?
Yes.
So this is not the same as the P prime on the whiteboard.
Sorry?
This is not the same as the P on the whiteboard, which is a PDM.
Yeah, so this is a good question. Yes, exactly. Yes. And for any am I saying the wrong? No, I'm saying the wrong thing. No, this is a PDF. Does this make sense? Am I? I'm not.
I thought the second order stochastic dominance was the integral of the CDF. No, but yeah, but this is the sum of the PDFs as opposed to the integral.
Yeah, you're right. That's the CDF. Yes, absolutely. Yeah, you're right. Sorry. Okay. For any convex, what this implies, though, if you ignore my confusion, what this implies is that essentially for any convex function, if P is a mean preserving spread of P prime, the expectation of F is higher under P than under P prime. Okay. Now, usually the way you study this in economics is that you think actually about concave functions, which are usual utilities, and then a mean preserving spread just corresponds to more risky lotteries because you have more variance. And then what you're saying is if you're a risk-averse agent and you're facing a heterogeneous lottery, a lottery with more variance, you're going to suffer. Your expected utility is going to be lower. Okay? So this would just tell you that under a lottery that has more variance, your expected utility is lower. Okay? This is this condition, effectively. But we're going to use it with convex functions, so that's why I'm writing it with a convex function. It's just the converse. Okay. Does this make sense, despite my confusion? Okay. All right. So let's increase the variance of degrees. So suppose that V dx is increasing and convex in D. And H, the distribution of cost, is convex as well, which would be captured, for example, if what you cared about was the average number of agents around you who are adopting, and H was uniform on some interval. And suppose that P prime, now we're looking at the underlying degree distribution, is a mean preserving spread of P. Then this, as it turns out, implies that phi of x is pointwise higher under P prime. Why is that? If you look at this formula, then notice that what we're doing here is basically this D times H is going to be a convex function, and we're just changing P through a mean preserving spread. So we could just use the definition of a mean preserving spread. Okay, so this is how it's going to work formally. So roughly what this implies is that increasing variance leads to lower tipping points and higher equilibria, and higher stable equilibria. Okay, what is some intuition for that? A mean preserving spread increases the number of high degree nodes. Okay? So if V is increasing, this one means that they would adopt in greater numbers. And therefore you would expect the tipping points to move down. It would be easier to get an explosion of the epidemic or the product or what have you, right? Because you have more people who are more likely to adopt. Now, why do we need this convexity? You need to make sure that the increases in the adoption rates from the higher degrees compensate for the reduction in adoption by this larger mass of lower degree agents. Because when we did a mean preserving spread, not only did we shift weight to higher degrees, we also shifted weight to lower degree agents, right? We sort of stretched the distribution. So we need to make sure that the increase in the action 1 adoption of the high degree agents makes up for the reduction by the low degree agents. And that's what this that's where the convexity comes into play. That's why we need convexity. Okay, so far what we talked about is kind of the underlying structure of the network. So we were thinking about between networks or between environments, because we were changing either the network through first order stochastic dominant shifts or these variance changes, or we were changing the cost distributions. Now what I want to think about is changing location within the network. Okay? And thinking a little bit more about the structure of the payoff itself. So, in that, yeah. Yes, in some sense, you could think about it
So
in
if
this way.
you assume
Yes.
like a normal
Right.
stochastic like econ increasing differential scale, we can't
You
get
could get it. You could even get it as a linear, like I mentioned, you could even get it when it's linear in B. But you're right.
But
I mean,
not.
you're right. You're right. Yes. Okay, so let's assume for a second that v of dx takes a simple separable form, where v of dx is just v of d times x. And now what we're thinking about is varying v of d. Why is this related to kind of the location within the network? Because in some sense, it's almost like asking if I could target particular individuals and make the product more appealing to them or immunize them against a disease, whom should I target? Whom should I change this v of d for? So in that sense, some subsidies, free products, immunization, all these things could be thought of as changes in v of d. Okay? So it might seem weird that I'm sort of thinking about changing people's preferences, but that's that's sort of the underlying story that I have in mind. So what we're trying to think about is whom would you want to reduce the v of d for? In a way. Or another way to think about it is suppose you have this sequence of v of d's, all this utility. How do you want to organize it? Do you want to make it increasing in d or do you want to make it decreasing in d? Now, if p d times d is increasing, v of d increasing raises phi of x, right? If p d times d, if this thing is increasing in d, then the higher vd, the higher vd is, the higher phi of x is, which would lower the tipping points. This corresponds to P being uniform. So for example, if P is uniform, if you think about the density is a fixed number. So a fixed number times D is going to be increasing in D. Okay? So this is the case for a uniform P. If PD times D is decreasing, then the reverse holds. So then if V is decreasing, it raises phi of x, pointwise. And that lowers stable equilibria and raises the unstable equilibria. Yeah?
I'm having trouble interpreting what would it mean to reorder V?
Yeah, so this is just a different way to think of whom do you want to subsidize. So how do you want to organize the subsidies? Do you want to give subsidies, make the V of D low for people who have low degrees or people who have high degrees? Now, kind of the first take of it, when you look at early marketing literatures, the idea was, you should target people who have high degrees. Okay? And now we're trying to understand whether this is actually the case for all distributions. And now, as it turns out, this is not the case, right? Because, for example, if PD times D is increasing, then you see that increasing V of D actually lowers your tipping points, right? So it depends. If you're thinking about an epidemic, this is a tricky thing, right? So it depends what you want to create, whether you want to create an explosion or you want the epidemic to die out. Right? Okay, and this is the case if P is a power distribution. This is this distribution that we talked about a fair bit yesterday. So like I just said, this goes against the idea that you want to target high degree nodes. And essentially what this suggests is that you need to think about not only one's own degrees, but also one's neighborhood's volume. So essentially what this corresponds to is thinking about who has a high volume of neighbors, not only who has a high number of degrees. So you think about also the degrees of your neighbors. What about adoption rates? So we want to know whether adoption speeds or slows down. When I started talking about diffusion yesterday, I show you all these graphs from the 60s or 50s that illustrated kind of an S-shaped adoption curve. So we want to know how adoption behaves as a function of the payoffs and the network structure and how it differs across different degree individuals. So as it turns out, if V is increasing in D, then we know that higher D's adopt at higher rates. This is the first observation we started out with. So adoption should kind of increase as you increase different D's. Let me just draw you a pictures and skip this analysis. So this picture corresponds to different degree agents under a power distribution, which we talked about yesterday, where the costs are uniform and V of D is just D. So we're looking at the linear utility function. The costs are uniform, so this satisfies all of the assumptions that I just talked about. And I'm showing you the curve of adoption for different degree individuals. So notice that this is the same pattern that we saw for the adoption of tetracycline, for example. So this is the adoption of antibiotics, and what this graph corresponds to is just adoption according to how many other doctors you're talking with. And what I showed you yesterday is that these curves were increasing in the number of doctors that people were talking with, sharing information with. Right? And this was the same pattern that was observed also in the Grillicus study of the hybrid corn. So this is sort of in line with the type of empirical studies that we have in this literature. Okay, so what's the summary of the diffusion stuff so far? First of all, networks differ in structure, and that captures some aspects by degree distribution. And the location matters. So if V is increasing in D, we saw that more connected adopt earlier and at higher rates. And they have higher expected payoffs as well. The structure matters as well. So lower tipping points raise stable equilibria if you have lower costs. So lower costs lead to lower tipping points. It's easier to get diffusion of the product if it costs less. If you increase connectedness, it's easier to get diffusion as well. So this corresponds to lower tipping points. If you have high variance under some conditions, we saw an explosion that's being easier as well. And we saw that whom you want to target for immunization really depends on the underlying structure of the network. Okay, so that's what I wanted to say about diffusion. I know this is a lot of kind of heavy details, but ask me questions either now or later, if there are any. So in the remaining time, I'm going to completely switch gears. And what I'd like to do is tell you about a bunch of models of network formation. So what I'll start out with is very simplistic two models of kind of mechanical models of network formation. And I'm going to choose these two models because they match the types of network distributions that we've been talking about throughout. So namely the Poisson and the power-like distributions. And then hopefully I'll have time to tell you a little bit about a slightly more strategic model of generating similarity between people who are connected. Okay, so let me start with kind of the basic models of network formation. So this will require some techniques that look different than what I just said. So I know this is a lot of equations and it's hard to sit through many hours of these things. So ask me questions or slow me down if this becomes tough. Okay, so let's think about a situation where you have a population of nodes, and each node gets born in each period. So we have one node that's being born in each period, and now we're going to specify how they get connected to the existing node. Now, di of t is going to correspond to the degree of node I at time t. Why does it depend on t? Because as more people get born, your degree may change. Namely, it's going to increase in these models. So di of I is just the number of links that are formed at birth. This is what happens when your agent I and the number of the neighbors you have at time I. And dit minus dii is just the number of links formed between I and the nodes that are born between I plus 1 and t. Right? These are all the nodes that you've accumulated between the time in which you were born and time t. Okay, so let's start with something that looks just like the Poisson, yeah.
So you cannot make connection with those who are born before you, but after you are born, not at the
Exactly. So every time someone enters the room, they choose a bunch of friends, and you have no say. You have a say only when you enter the room. Yeah. So here's the kind of the analog to a Poisson formation of the network. So recall yesterday the Poisson, the way we thought about the formation was that you just had a random probability P of creating a link between any two individuals. So now the analog in this world is going to be the following. So let's start with m plus 1 nodes who are all connected. They were born in period 0 through m. And now from m plus 1 and on, each newborn node connects to m random nodes. Okay, so it just, and you enter the room, you randomly pick 4 friends or however many people you can go drinking with, and these are the people who will be your friends. Okay? And now this number may grow because new people who come in may connect with you. Okay? But they follow this process as well. Now, tracking all of the precise distribution of degrees here, kind of tracking the probability of having each degree, is going to be sort of complicated. So what I'm going to focus on is expected degrees, essentially. And if I had a lot of time, I would follow through kind of this discrete process and show you how to analyze it. Because I want to go through it quickly, I'm going to do a continuous time approximation of this. Okay, so I'm just going to write an ordinary differential equation that will correspond to the process I just described. Okay? So let's think about how to write this differential equation. Well, the initial condition is that each newborn person has m connections. These are these m random links that you're creating when you're born. Now, in each period, you're randomly choosing getting m over t connections. Why is that? Because there are t individuals out there at time t, and then the newborn chooses m connections out of these t's, right? These t individuals that are in the room already. So your probability of getting a new link is m over t. Okay? So the change in each period t is just m over t. Does this make sense? Okay, so now, yes?
We assume that we pick that the newborn picks randomly uniformly?
Yes,
Okay.
yes, yes. Yeah, and we'll soon change that. But for now, it's uniform. So now, the entire degree distribution is going to be determined by this differential equation. So this ordinary differential equation has a solution. If you solve it, you get this thing. So it's something that depends linearly on m, and then on the log of t over I. And now we can kind of depict the degree distribution that will emerge, kind of from all the expectations that we have here. We can see what fraction we expect to have of each degree. So first of all, let's say for any d and time t, the I that has an expected degree, what's the time of birth of an agent who has precisely that degree? Okay? Because anyone who was born before that will have a higher degree in expectation, because degrees here are just increasing. As you stay more and more, and as you live longer, you get more and more degrees in expectation. Right? So this threshold will allow us precisely to capture the distribution of degrees.
Sorry, can you explain that again?
Yeah. So now I'm trying to look at the time t and figure out how many people have a degree which is less than or lower than b. Right? So in order to do that, these are all the people who are fairly newborn, right? Because they have a degree which is lower than something. If someone has lived in the population the longer you live in the population, the higher your degree. So what we're looking for is precisely the threshold, the time of birth, such that your expected degree is this value. So everyone who is born after that time would have a lower degree in expectation, and everyone born before that time would have a higher degree in expectation. Does this help?
This is your expected degree in the fully realized network.
Exactly. Exactly. Does this make sense? All right. So again, if we look at the distribution here, we would get that the people who have a degree less than this element D are precisely the people who are born after this threshold individual. Okay? This threshold individual was born precisely at the time when their expected degree is D, so anyone born after them is going to have a lower degree. Right? So this is precisely the fraction of people who will have a degree lower than D. So this gives us the distribution. And if you solve it out, I won't take you through the algebra, what you get is something that looks precisely like the, or not precisely, but it sort of looks similar to what we got from the Poisson network. At least we have this exponent here. It's not precisely, but it's almost. So this is one way to form networks. This is if we sort of take this Poisson dynamics seriously. Now the other type of networks that we talked about are power networks. The way to get them, the kind of the best-selling hit for a dynamics there, is a model that's called Preferential Attachment, which was suggested by Price in the 70s and revived in the late 90s by Barabasi and Albert. And the idea here is that nodes attach randomly, but with probabilities that are proportional to degrees. So if you have someone that's very popular, if you enter a new room and there's someone very popular, you're more likely to attach to them. That's the idea. Yeah.
Sorry, just going back to the way you form Poisson networks. All this makes sense, but unless you can say that this is the only way in which a Poisson network can be formed, and you have some reason to believe that this is the underlying mechanism, why would you suppose that this is the way?
I wouldn't. I don't think this is necessarily a good model of behavior. Unfortunately, this is almost like a teaser for you guys. Unfortunately, it's very technical and it's not very appealing. But there aren't very many models that really correspond to behavior. So most of the models of network formation, this is a good depiction of them. This is a good, or a caricature of them. They're very mechanical. And you're absolutely right in highlighting that. So it's one particular model. There's no behavioral reason to believe that this is how people actually act. And you know, but we can solve it. It's, yes?
Yeah, so to follow up, is it important that nodes are like arriving one by one and then their edges are forming, or could we just say, here's n nodes, let's start throwing edges down? Does it matter?
So if we just throw edges down, you're back to the original Erdos-Renyi construction, right? That was precisely the premise. So we know how to solve that. Now, this was supposedly a more kind of dynamic behavioral interpretation, but like Kaushik said, it's not a particularly appealing dynamics. And I'm very sympathetic to that. Okay. So I just want to show you kind of the best-selling the caricatures of the best-selling networks that we have out there. There are a bunch of other models that I won't have time to go through. I just want to give you a taste of what these models look like. Okay. And really the best-selling ones are ones that correspond to the Poisson and the other one that corresponds to the power degrees. So just to give you a glimpse into that, it's a model that is just like the one before, but now the probability of matching to anyone in the room depends on their own degree. Okay? So in other words, at time t, the probability that I receives a new link depends on i's degree. This is just a normalization of everyone else's degrees. Is this clear? Okay. Now let me skip all the formulation of this. But if you solve it out in precisely the same way that I just solved the Poisson thing, so you can repeat the same exercise. This is just algebra, so unless there's particular interest, I won't go over it. What you get is a density that corresponds precisely to the power distribution with degree 3. And this is sort of interesting because, as I showed you yesterday, a lot of these power degrees that we see in the empirical distributions have a degree that's somewhere in between 2 and 3. So we even nailed the degree down nicely. Okay. But again, this is a very mechanical model, so there's no strategy here. And there's no strategy, there's no behavioral underpinnings, it's very mechanical. Okay, so what I want to do now is move to a different type of network formation model, which is part of a new wave, I think, of network formation models, which is a bit more strategic than that. But it will give us less structure. The cost will be that it will give us less structure on the precise architecture of the network. And the motivation for this is this observation from sociology that people kind of tend to connect to people who are similar to them. And that's a phenomenon that's commonly called homophily. It sounds like a disease, but it isn't. It literally means love for the same, and it was coined by these two sociologists in the 50s, Lazarsfeld and Merton. And this is observed across the board and across fields. So people with similar, people who are connected to one another tend to have similar political opinions. They tend to come from similar demographics, from similar economic backgrounds, and so on. Now, there is kind of a problem in this literature that I would like to highlight kind of from an empirical perspective, which is that if I look at two friends and if I see that Tim and Ariel are friends and they have the same political opinion, it might be because they selected one another for this reason. Or it might be because they hang out so much that they change their mind. So if we just see this correlation, we don't really, it's a chicken and an egg. We don't really know what precedes it. So this is where looking at stuff that's non-malleable, like race or height or things that you can't change, is really useful. And we observe this homophily also on these dimensions. So just to give you a bunch of kind of as a break from these formulas, this is a table that comes from Dutch high school. And what they did here, this was a very multi-ethnic high school. What they looked at is, for example, if you look at the Dutch students, they looked at the percentage of their friends who are Dutch and the percentage of Dutch students in the overall population. Okay, so if they just chose friends at random, the distribution would correspond to the population distribution. But if you look at the actual distribution of friends, you see that they're choosing more Dutch friends than there are in the population. And if you look at the Moroccan students, for example, 27% of their friends are Moroccan, even though in the population of students, there are only 5% Moroccan students. Okay, and so on and so forth across these ethnicities. So it seems like they're selecting the same ethnicity at the same rate. Now, if you go back to this study that I was involved in in the girls' school in Pasadena, so that this is more local to me, and recall that the different colors here corresponded to the races of the different girls. So this is just a connection between the girls, and blue corresponded to Caucasian, black to Asian, red was the mix, and yellow was anything other. Yeah.
Is there any significance to larger dots?
Yeah, larger dots just correspond to more degrees, so higher degrees, so
Okay.
more connections. This won't matter much right now for the discussion right now. Okay. Now, just eyeballing this, you may be able to tell that kind of the blue dots tend to be connected to one another, and the black dots, at least, look sort of connected to one another, but it's hard to see from just the graph. It might be somewhat possible to see. So what we did is a similar exercise, but not only with respect to race, also with respect to other things that we elicited, like confidence, popularity, height, etc. Okay, because we got a lot of things from these girls. So what you see here is these percentages correspond to percentages of girls. For example, this 55% means that 55% of the girls, or with respect to, let's pick 60%, it's more stark. 60% of the girls had girls in their neighborhood that were of the same race at a higher rate than in the entire population. So this is kind of the percentage of girls that exhibited homophilic friendships with respect to race. Okay. So what you see here is a substantial, over 50% of the girls exhibit kind of these homophilic friendships across different things that we don't think are particularly malleable. Not all of them, at least race and height. I don't know about confidence and popularity. This is a different way to look at it with respect to race. So what we see here is if you look at the white, this is just kind of breaking down the table of the Dutch high school effectively. So what you see, each dot here corresponds to kind of the actual distribution of whites as a function to what you would expect in the population, accounting for the number of friends that the girl had. Okay? So any dot that is above the 45-degree line essentially corresponds to a situation where the number of friends that you had from the same race exceeded the population distribution. Okay? So this is the type of homophilic preferences that we're thinking of. Questions? Yeah.
That's probably not at all on the point, but I was wondering the confidence. It was one of the four that was, to me, the least objective one. How did you measure it? Was it perceived confidence or was it self?
That was a self-report. Okay. So, and we asked it in different ways. Psychologists have devised different ways to elicit confidence. So we used their techniques. But you're absolutely right. That's probably not the thing I would focus on with respect to homophily. I just mentioned it because it's sort of interesting. You know, we looked at a bunch of other things which were sort of funny. For example, girls wear braces in the U.S. So you can look at whether they tend to befriend people who wear braces, but the statistics there is weaker. Other questions? Yeah.
What age? How old are these girls? Was their height changing rapidly, or?
The height. This is a school that takes them from preschool through what is it? 6th grade. I'm always confused with the middle school and high school in the U.S. Okay, so the question we want to ask with the models, taking this into account, is basically, where is this coming from? Now, there are different reasons why you'd think that people would exhibit kind of these tendencies to connect with one another. So the main goal here was the idea that people choose whom to interact with, and once they choose the group of actors they interact with, they actually place some sort of strategic interaction with them. So what we want to really understand is the structure of endogenous group when the individuals who participate in the group ultimately play some game on it. Okay, so the goal is to provide a simple, today I'm going to give you, I just want to give you a flavor of the type of model, so I'm going to focus on an information-based model. Just to analyze how individuals choose peers. But I'll try to mention as I go along where you could generalize it. So I'm going to think about a very, very simple game just to illustrate to you the forces that may make the selection into the group kind of important. But this matters, by the way, for any game that you can think of. Even if you think about an auction, you might want to think about who are the people who are selecting into the auction. And this is something that we don't commonly think about. So individuals here are going to differ in how much they care about each of two dimensions. So you can think about it as savings and education, different food and music, and so on and so forth. And individual in a group are going to play a public good game of a particular sort. So ultimately, essentially the idea is I have a bunch of friends and we're ultimately sharing information about stuff. And some of my friends care more about food, some of my friends care more about music, and therefore they read different things, and when I interact with them, I get different types of information. And we want to understand the elements that determine the emergence of homophily, or a different disease, heterophily. And in particular, information gathering costs, which I won't have time to talk about, group size, and different population attributes. Okay, so here is the most simplistic model in this setting. So think about a situation where you have two issues, A and B, which take two values, 0 or 1. Okay? And they're determined at the outset. So it's almost like you have a choice between there are two restaurants and one of them is superior to the other, and two concerts and one is going to be cooler than the other. And the probability ex ante of each value is equally determined. That doesn't matter, it's just going to make things simpler. There are n agents in a group, and each agent is ultimately going to make a decision on each dimension. So it's just like ultimately you're going to have to choose which restaurant to go to and which concerts to go to. But you may care less about one or the other. You may not care about which restaurant you go to, or you may just not mind which concert you go to. Each agent is characterized by a taste. So this is going to capture how much you care about one dimension or the other. So the utility of agent I from choosing the action V, this is this guess for each of the dimension, when the realized states are A and B, is given by this. So what this means is that you get Ti if you got things right on dimension A, and 1 minus Ti if you got things right on dimension B. Okay, so Ti basically captures how much you care about getting things right on dimension A as opposed to dimension B. So before choosing the actions, agents have access to information. And now this is where the game comes into play. So think about a situation where you have 1 hour to read the newspaper in the morning, and you need to decide whether to focus on the restaurant section or on the entertainment section, which will give you some information on music. So you have access only to one signal, which will give you with some probability the superior option on the corresponding dimension. Yeah?
Are A and B correlated?
Are what correlated?
A and B, the events?
No, everything is independent and the signals are conditionally independent. Yeah. So the types of signals, so this is the simplest case, and then we can think about how to extend it. So what does an information source do for you? Well, depending on whether you chose to read the dining section or the music section, with some probability it's going to tell you what the realized state is. So for example, if you chose source alpha, it gives you precisely the state A, which state has been realized, with some probability Q alpha. And with probability 1 minus Q alpha, you learn nothing. Similarly, for source beta, it provides you the realized state B with some probability Q beta. Okay. And signals are, like I said, conditionally IID. So everything is as simple as possible.
So it either gives you nothing or the true state of
Yes.
it doesn't mislead you.
Yes, exactly. Now, what makes a group? A group it corresponds to a situation where after the information sources are selected, everyone in the group shares their information. So basically, all the information is made public. So if K agents are choosing the signal, does this make sense actually, the choice of the... Okay. So if K agent choose X equals to alpha, the probability that the state A is revealed is just this probability. Right? Because with probability 1 minus Q alpha to the K, this is just a probability that no one gets an accurate signal. Right? So 1 minus that is the probability that at least one person gets the correct signal. So the probability of making the right decision on A is just 1 minus 1/2 of this thing. Why is that? Because if you don't get a precise signal, with probability 1/2, you're going to get things right anyway. Right? So this just corresponds to the probability that you get things right with K signals. Okay? And similarly for X equals to beta. So the methodology is as follows, and this would be, I'm doing it for a very particular game here, this silly information collection game, but this would be true for any sort of public good setting, and in fact you can think about a very general way of kind of stating the utilities here. And ultimately what you're doing here is the following. Given a group of agents with taste parameters, we can solve for the equilibrium, for the type of information sources that I would select in equilibrium. Right? So we have a very simple game, this information selection game, and given that they know everyone else's types, we can just compute the equilibrium there. Then we can step backwards and say, well, given a group of size n, everyone is foreseeing what will occur with every distribution of types. Which types would they select to enter? So what types of friends will they select? Okay, so this is sort of a two-stage game where at first you select your friends, and they're characterized by a type, and then you play this information collection game. So we're going to characterize the optimal group choice for each agent T, and then characterize the stable groups. And a stable group is a group that is optimal for all of its members. Okay, so that's a group that everyone is happy to be in. So this is where the network formation is coming into play. It's not fully a network. I'm not going to draw a graph here, but I'm just going to tell you which types of friends are going to be more appealing to you. If you have a neighborhood of n agents, how is it likely to look like? So I'm going to focus on free information now and talk a little bit about the optimal groups. Okay. So consider a group of agents, T1 through Tn, and let's assume that T1 cares most about dimension A, agent 2 cares a bit less, and so on. And the equilibrium sources are just going to correspond to x1 through xn. So this is just whether each agent chooses to read the dining section or the entertainment section of the newspaper. Now the first lemma just says that everything is well behaved. We don't have multiple equilibria outcomes here. You may worry if you have multiple equilibrium outcomes, then how you select the group sort of entails in it some sort of selection process. We want to sidestep that for now. So this lemma just guarantees that in this type of game, we have a unique equilibrium outcome. And namely, the way you can characterize this equilibrium, the outcome, is one in which the people who care the least about dimension A choose to learn about dimension B, and the people who care the most about dimension A learn about dimension A. Okay, so basically, there is some threshold such that the people who care most about dimension A learn about dimension A, and the people who care most about dimension B learn about dimension B. And the number of signals that is collected on each dimension is uniquely determined. Okay, so let n alpha of t be the optimal number of alpha signals for a type T. So this is as if they have access. Suppose they could choose for their friends the signals that they take, or choose for their friends the part of the newspaper that they read. Then this would specify precisely how many of them would read the dining section and how many of them would read the entertainment section. So essentially, NF alpha, in terms, kind of in economic terms, equates the marginal returns from an alpha signals with the marginal returns of a beta signal. So for any T, the class of optimal groups, so if you just think about one individual who chooses the optimal groups, I'm still not in stability. So I'm just one individual who has full leverage. She would want at least NF alpha T. These are the number of people who are choosing the alpha signal to have a sufficiently high T, to care enough about the A dimension in order to choose the alpha signal. And she would want the rest of the individuals to care enough about the B dimension to choose the beta signal. Right? That's how she would choose optimal groups. So essentially, she would have some threshold T such that she would want to assure that n alpha agents are choosing care enough about dimension A, right? So they're to the right of this threshold. And there would be another threshold that would correspond to the rest of the agents who would care enough about dimension B in order to choose the B signal. So the agents that are in between these two thresholds are going to ultimately correspond to stable groups because these are precisely the agents who will agree with this allocation. Or let me describe it in a different way. The main proposition here is going to be the following. So this is going to be the main proposition that I'll show you. I'll give you an intuition for this, and then I'll release you. So that's where we're headed. So there exists a partition of the interval such that essentially a stable group is one where all of the individuals belong to the same interval from the partition. So this is the full characterization of stable groups here. So there is some partition, and the group is stable if and only if everyone in the group belongs to the same element of the partition. Now, furthermore, the intervals are wider for moderate types, and they're narrower for more extreme types. And the same characterization would hold if each agent were to acquire more than one signal, because essentially we could look at an analogous problem with n times h signals. So this is just kind of an easy extension. Okay, let me give you a graphical intuition of where this is coming from. So let's think about the graph that corresponds to the optimal number of alpha signals for each individual. Okay. So on the x-axis, we have the type of the individual. This is this parameter that captures how much you care about action A. And on the y-axis, we have the optimal number of alpha signals. Now, if you have a type which is 1/2, approximately the marginal contribution from an alpha signal or a beta signal kind of should be equal to one another, so we would expect that the optimal number is precisely n/2. Right? Now, as you care more and more about dimension A, you want more and more alpha signals. Now, there is a bit of a subtlety here because these information protocols have decreasing marginal returns, so the more alpha signals you have, the lower the marginal return of an extra signal. So there are two forces at play. So you need to show something technically to illustrate that this in fact has this sort of shape, but it does. So now let's think about how to construct the stable set. Stable sets are situations in which all of the individuals are happy to be in that group, right? So these correspond to situations in which all of the individuals agree on the number of alpha signals that are being collected. So what does this mean? This means essentially that these are the intervals that are just projections from the intervals on the y-axis. So let's look at all of the types that correspond to an image here which is between 0 and 1. This is precisely all of the individuals that agree that collecting all of the signals on dimension B is the right thing to do. So this is going to be one element of the partition that corresponds to a stable group. If we look at the projection that corresponds to elements between 1 and 2, these are all the types that agree that the optimal number of alpha signals is 1. Right? So this partition is going to, this element, this interval, is going to correspond to the individuals who all agree as well. Right? So any n individuals in this interval is going to be stable as well. And so on. So we can construct these things. Now notice that for this partition structure, all I needed here is for this curve to be increasing. Right? So far I haven't used the shape of the curve. Right? So in fact, for this sort of curve to be increasing, you need very minimal restrictions on the types of utilities that are underlying things here. Now where does the shape come into play? The shape comes into play when we're thinking about which groups can be the most heterogeneous. Because notice that because the curves are concave initially and convex ultimately, what we get is that at the extremes we have very small intervals, just from this picture, and when the curve is very flat, it's going to correspond correspond to very wide intervals. Which in turn means that moderates, stable groups that contain moderates can be rather heterogeneous, whereas stable groups that contain extremists are going to be kind of very, very narrow. Now, as it turns out, this thing doesn't actually, you might think that as you take n to be very, very large, if you have a group that's very, very, very large, you might think that you can select people who are just more and more similar to you. This is actually not the case. As it turns out, even if you take n to be infinitely large, you're still going to get these non-trivial stable sets. So this partition is still going to kind of hold water even for very large n. So I'm going to skip the formal thing. Okay, so what did I show you here? So first of all, there are cohesive larger intervals for moderates and narrower for extremists. Now, the implication is that, for example, geographical constraints decrease when you have kind of access to whomever you have more access to choose your groups. We would expect the homogeneity to increase, and that should be stronger for extremes than moderates. And there is some evidence for that, actually. Both Lind and Lind actually looked at the introduction of the automobile in the US and showed how it affected clubs and memberships and how it affected the distributions of types of different sorts into these clubs. There are also some studies that look at the introduction of the internet. For example, even on co-authorships in economics. So if you look at co-authorships after the introduction of the internet in the 90s, you see co-authorships that are much more homogeneous than before. More co-authorships, more homogeneous. For moderates, heterogeneity persists for large group size. So yeah, that's basically it. Now, empirically, deducing preferences directly from individual actions is problematic. It's really important to account for public goods that are obtained from the friendship. So this is kind of suggests that we really want to inspect the game that's being played in order to deduce something from individual actions. Because we need to think about the other groups that they're interacting, the other group members that are interacting with. I think we're out of time.
Questions?
Yeah.
So in this paper, the group size n is being held fixed, right?
Not in all of the paper, but in what I just told you, yes.
Okay.
Yes. So I think what you're suggesting, which is a really good point, is that here n is fixed, but in principle you might think there are two reasons to relax this. First of all, you might think that for certain groups an additional member is more valuable than for other groups. So that's one thing. The other thing is that here we're assuming something very, very stark, which is any group that you can imagine is available to you and is a potential deviation in your mind, right? But if we think about a finite population, if I just try to create friendships in this room, it's not that any constellation of group memberships is available. So really you want to think about the partition of a finite group of people. And you can kind of replicate this sort of analysis for this setting as well, and very similar insights emerge as it turns out. Yeah.
So what is it that's coming out of the fact you've got an information acquisition model more rather than a more general public good where people want to form groups with others who have similar tastes, so you look at a value of the public good that's optimal for everyone?
What happens with information?
Yeah, or why is this a model of information acquisition specifically?
So here the information was free. Information costs introduce interesting forces here.
Or, I mean, not as costly, but you could imagine other models will also predict people want to form groups with others with like preferences, right? So you've got a bunch of people who are going to form into groups, and then each group is going to spend some time at dinner and some time in the park. And so if I have a preference over how much of the afternoon we spend at dinner and how much of the afternoon we spend in the park, I'm going to want a group with other people who have the same preference so that we'll all agree and do what's optimal for all of us.
Right, so there are different reasons for why you think people would hang out with people who are similar to them. So So some of it is just plain activities, like you mentioned. You can think about different settings. Those of you who know the Crawford-Sobel model of communication know that it's easier to communicate information to people who are similar to you, who have more aligned preferences. So there are different kind of models out there that would suggest to you similarity. This is a simple class of particular types of preferences that generates this as well. And the advantage is that it allows you to also get some information about when this similarity emerges, kind of how heterogeneous the group can be. And that you can see either through this or through kind of introducing information cost actually turns out to be amazing.
So I guess my question was, is there some intuition for how the structure of the information acquisition is driving the kind of different levels of heterogeneity?
Right, so this really depends, in principle you could have a general utility that just has people investing in different dimensions of different tasks, and you could kind of see the interplay between these two things. So some of what's going on here is these decreasing marginal returns on each dimension, and that's driving part of the thing. And you need something about the interaction between the two dimensions. I can tell you details later.
Well, I want to thank Leeat again for participating in the semester.